Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, good afternoon. We will continue our homological algebra from last lecture, and in this homological algebra I will not prove almost anything, but I want to make it self-contained by giving definitions and also some examples. So, for example, last time we saw what is the projective module. So, let us recall briefly. So, A is our fixed commutative base ring, and we are studying the category of A modules. And the idea is to get information about the ring from this category. That is the main idea. Okay, so module P is called projective. If we saw definitions was two equivalent conditions. So, home A P dash, this functor from category of A modules to category of A modules is exact. That means it maps exact sequences to exact sequences, and because this home is left exact, what fails is the right exactness, and that is spelled out in the definition. So, this is equivalent to saying for every surjective map given M double prime to 0, this means surjective, this is phi, and given any A module homomorphism from P to M double prime F, we should be able to lift it here, so that this diagram is commutative. So given this, there exists F bar from P to M such that with phi compose F bar is F. Then you call that module is projective. This is also equivalent to saying that P is a direct summand of a free module, and free module is the module which has a basis. In general, every module may not have a basis over arbitrary commutative ring. So, if a module has a basis, then you call it a free module, and then one proves that the number of elements in a basis is constant. I mean, it's any two bases have the same cardinality, like theorem in linear algebra. And for this, commutativity of the base ring is very, very important, because this statement is not true for non-commutative rings. So, there are examples of a modules, free modules over a non-commutative ring, in which they may have two bases, may have different cardinalities. But anyway, our problem is, because we are assuming all the way it is commutative, so we do not have to worry about it. So, actually the third part of the definition, I mean third condition, equivalent condition of the definition tells you which are the examples of projective modules. For example, so some examples. free modules are projective. Free modules are A-projectives. Because it's a direct sum of itself. So, just to show that there are examples of a projective module which are not free. So, for example, if you take the base ring to be Z mod 6, then Z mod 6 is same as a ring isomorphism, Z mod 2 cross Z mod 3. So, therefore, this is a free module, A is a free module over itself, and this is Z mod 2 as a module over Z mod 6, it is a direct summand, but it can't be free, because if it is free, it will have a basis, and then the basis, I mean any free module will have cardinality equal to cardinality of the base ring power to the rank of the module. So, it will be, in this case it should have at least rank 6, but it has the cardinality 6, but it has only 2. So, therefore, Z mod 2 is projective Z mod 6 module, but not free. Okay. Another, I will mention this because this topic is very interesting, and also right now, last many years, it is a very frontline research topics. For example, this is regarding when are the projective modules free. So, when are projective modules free? So, for example, we are interested in a polynomial ring, for example, even for a polynomial ring over a field. So, even when you take A equal to, so in this ring, actually this question originated in 1955 by J.P. Serre, and his motivation to raise this question was the following. So, look at the polynomial ring in n variable over a field. So, this is a very special ring. So, he asked the question, is every finitely generated projective module over kx1 to xn free? And this question was there for a while, and ultimately the proof came only in 1976. Two independent proofs came, one by Suslin and the other by Quillen. This answer is yes. But why did he ask this question? That motivation I want to raise here, because it is interesting. So, remember this polynomial ring kx1 to xn, study ideals etc. in this you have seen ideals, prime ideals, maximal ideals, study of this in this ring, that was closely associated with algebraic geometry, and namely spec kx1 x2 xn. This topological space is the Zariski topology. This is also called, some people, the affine n space over the field. This is also usually denoted by A n k. This is not k power n, but the spectrum is also known as affine scheme. Actually, it is called affine scheme. So, the algebra, this is the algebraic part, this projective model being free is an algebraic part. So, what was the geometric part? The question he formulated, this algebraic question was formulated from a geometric motivation, namely, so you would have studied in algebraic topology for example Rn. This is the Euclidean the topology, the usual topology on Rn or Cn. This with usual topology, these spaces are so called contractible. If you do not have much knowledge, I think you can ignore it, but those who have or want to have, this is very interesting. So, these spaces are contractible. Contractible means identity map is homotypically equivalent to the constant map, that is contractibility of the space. So, in particular it implies pi 1 for fundamental group is 0, trivial. So, now if you want to formulate this contractibility to this is our topological space now, and then you can also, one would like that the analog here holds. So, that means this topology, this spectrum with a Zariski topology, is it a contractible space? That is the question. And this question, when he converted into algebraic language, it became projective models being free or not. So, that is why, and beside this affirmative answer to this question will have lot of consequences in algebraic geometry. For example, this is also connected to the following fact. So, for example, when you take curves, algebraic curves in 3 space, let us say C3. So, typical examples that we know are, for example, if you take a cylinder and cut it, or cone and cut it. So, conic sections in this. So, curves in 3 space, the question is whether are they defined by 2 equations. So, if you say irreducible curves, they will correspond to the prime ideals P in the polynomial ring in 3 variables, and they will be height 2, height of P is 2, because the dimension of C x y z mod P should be 1, because they are curves. So, height should be 2, and then so they will need at least 2 equations to define, but the question is whether R2 is enough. So, that means the question is translated into completely algebra by given a prime ideal P of height 2, height P is 2, is P the radical ideal of 2 ideal generated by 2 elements, because if it is so, then in the geometrical language V of P will be equal to V of F intersection V of G. So, that means this curve is intersection of 2 surfaces, but this answer is till today not known even for C and 3 space. So, this is not known in general. Yeah, this is called set theoretic complete intersection. This is called set theoretic complete intersection. It is only set theoretically, not the ideal theoretically. Ideal theoretically, the answer is easier to give examples. So, this is closely connected to projective modules being free. So, more than that I will not go into that, because only thing I will say that projective modules over polynomial ring in n variables over a field are free. So, therefore, when one looks, for example, one cannot look over polynomial rings over a field. Okay. Now, next is, see, we are trying to define a homological dimension. So, we are by using homological algebra, we want to define what is the homological dimension of a module. So, first is note that given any module M over A, you can always write this M as a quotient of a free module. If you take any generating set, take a free module with that basis and map the basis elements to the generating set. Now, you can repeat this process. That means, you look at the kernel and write kernel as a quotient of a free module, and that way you can generate, you can cook up a sequence which is exact sequence of A modules, and all these free the modules are free, these are all free modules. In particular, they are projective modules. Such a thing is called a projective resolution. So, one might do a little bit better by not what is called minimal resolution. Minimal resolution. So, that is called a projective resolution. So, what we know is every module has a projective resolution. Every module you can write a resolution where each member there is a projective module. Okay, now given this, a minimal means, so minimal resolution makes sense only when the ring is local. That means, the image should not be contained inside the m times, that you choose every time the minimal system of generators. So, that means under these maps that m times the next one. So, that okay. So, I will come back to it when we calculate something. So, every module has a projective resolution, and the projective resolution is usually denoted by P dot and this map P dot what do I call it, epsilon. This is the projective resolution of M. So, I have now when I apply home, if I apply now the home functor, now I have to be careful because covariant contravariant. So, if I apply now, if I apply home, all these you can, all the proofs you can find in this TFR pamphlet number 5. Okay, there are two things I want to define now. So, we have a projective resolution, and so that is usually denoted by P dot epsilon to M. This is given. Now, if I tensor this resolution with some module n, tensor over n, if I apply this functor, then I will not get exact. So, I will get only a complex. So, that means I am looking P dot this to M tensor n A, and this part will remain exact because tensor is right exact. So, the surjectivity will be kept. So, this when I tensor this from P0 tensor n to M tensor n, that part will remain exact. Earlier it may not remain exact. So, when I take the homology there, so Hn of P dot tensor over a n. These are what, how do I calculate this? At each stage you look at kernel mod image. So, this is at if I take at nth stage means I have to take nth. So, this is at Pn tensor n over a to Pn minus 1 tensor n, and earlier one is Pn plus 1 tensor n, and we are looking at the kernel here mod image here. So, this is kernel of, let us say, Dn tensor identity mod image of Dn plus 1 tensor ID. This is nth homology of this resolution. This has a special name. This is called Tor n m n. This is by definition Tor m n. And now there are several things to check here. Namely, one, somebody may start with a different projective resolution. So, we have to check that this definition does not depend on the projective resolution. So, I will only hear that, I will only say that check that this definition does not depend on this projective resolution. And similarly, when we apply now, the other functor that we are interested in the home. So, when we apply home, also we will get, and there are several properties of this Tor and X. Now, you apply home A dash n. Now, this is the tensor functor was covariant, this is contravariant. So, the arrows will get reverse. So, it will now start the other way. So, it will start with, and 0 is left, home is left exact. So, this is 0 home A m comma n, and then home A comma P 0 n, and so on. In general, this should be home A P dot n. Now, it is a long exact sequence. So, you get therefore a complex again, and now we can again take homology, but as we said, when it is on one side of the 0, the suffixes, the n is denoted down or up. So, like Tor n, these I have denoted down. So, here in that case I should denote it up. So, that homologies or cohomologies, they are denoted by x n m n. So, this is by definition H n of home A P dot n. Again the same, that is kernel by image. No? And again now here this does not depend on P dot. So, this definition does not depend on P dot to m. So, if you take suppose a different projective resolution, then you get these modules, and they are A modules. So, okay, now let us summarize and then I will extract the properties of this module that we will need to use for our calculation. So for two modules M and N, we have attached the first, which we came from the tensor product, that is Tor N Mn, and these are also A modules. And not only that, you remember last time when we had a complex and then when we wrote the homologies, it had a long exact sequence and a connecting homomorphisms. So this one, these Tor different suffixes are connected to each other by that long exact sequence. And similarly, we have this X N Mn, these are also A modules, and if Mn are finitely generated, these are also finitely generated, because they are coming out of, however the Tor and X are coming, they are coming out of either applying home or tensor product and taking the quotients. Quotient means the submodules and the quotient modules, and all these, if your base ring is good Noetherian, then all of them are finitely generated. Therefore, all these modules are finitely generated. So, okay, so one more thing, then so here remember we have taken the projective resolution for M and tensored with N and took the homologies. So, but one could also do this by taking a projective resolution of N and tensoring with M, but these two results will be same because the tensor products are commutative. Now, M tensor N is isomorphic to N tensor M, so that they will, the resulting modules will also be the same, isomorphic. But in this case we cannot do that, because home Mn is not home Nm. So either you resolve this M projectively and then take the homologies, or there is other way which is more difficult than these projective modules, namely take the injective resolution of N and then apply home and then do the operation. But you know, for a module to prove there is a projective resolution is much more relatively easier than proving that every module has an injective resolution, because the structure of injective module is much more complicated than the projective modules.